This is lesson 3 of industrial instrumentation, and we will continue with the dynamic characteristics of a system, especially second order systems. Already we have discussed about the first order system. Now we will consider the dynamic characteristics of a second order system. Now contents of these lessons are the dynamic characteristics, the response of a second order system for step, ramp and sinusoidal input. We did it for the first order instruments, we will do for the second order instrument. Also we will solve some problems on the first order and second order instruments. At the end of this lesson, the viewer will know the characteristics equation of a second order instrument, responses of a second order instrument. Now, second order system, a sensor that is modeled by a second order differential equation is called a second order system, quite obviously. How will I know whether it is a first order or second order? If I go look at the response, and if the characteristics, if the output is coming which is supposed to come, because for some calibrated instruments I can tell whether how the response should look like. If it can't model by the first order instruments, we have to model by the second order instruments or higher order instruments. Now, accelerometers, diaphragm, pressure transducers, all these things will be discussed later. Mercury in glass manometers are few examples of second order system. Now, second order measurement system can be written as A2 y double dot plus A1 y dot plus A naught y equal to B naught x. Now, if I go back to our differential equations or the nth order differential equations, which looks like this. Nth order differential equations looks like a n dn y by dt n plus a n minus 1 dn minus 1 y by dt n minus 1 plus so on plus a1 dy by dt plus a naught y equal to b naught x. Now, you can see here that if I put n equal to 2, so we will get 3 terms which looks like A2 y double dot A1 y dot plus A naught y equal to B naught x. Quite obviously, as we know, all of us know that y double dot is nothing but d square y by dt square. Similarly, y dot is equal to dy by dt. Now, this equation can be written as or rewritten as y double dot upon omega n square plus 2 xi upon omega n y dot plus y equal to v naught upon a naught into x. Or I can write y double dot upon omega n square 2 xi upon omega n y dot plus y equal to kx. K we know that in the case of first order systems also, K is basically the static sensitivity of the system, which is equal to B naught by A naught. Now, we have introduced some new terms. Let us look at all these terms. First of all, omega n. Omega n is equal to under root A naught upon A2, which is undamped natural frequency of the system. We have xi equal to A1 upon 2 under square root A naught into A2, which is damping ratio of the system, and K is the static sensitivity of the system. Now, we will see that this damping ratio of the system, that means xi, will play important role for second order system. Depending on the value of xi, you will find that how much hump will be there in the systems. Typically, you will see in future that in the second order system, in a system that xi usually we put the value of 0.65 to 0.7, it lies between, because we cannot make xi more than 1, then in that case it will be overdamped systems, and we cannot make xi equal to 1 also, it is critically damped system, because if it is critically damped due to aging, because ultimately you know that all omega n xi k depends on some physical system, that means some resistance value, some capacitance value, some spring constant. Now due to aging problem this will change obviously. So I do not want my system should be overdamped, no, I mean we never want, until unless we are forced to. I will give some examples in future, you will find that sometimes even though we are saying that the system is underdamped, it will not be underdamped due to the change of the value of xi. So always will try to make xi at least 0.65 to 0.7, so that I will get at least one overshoot, then we will come back to the rest position. The homogeneous solution of the equation 1 which we have written will describe the natural and intrinsic response of any system. The output response will depend on the roots of the characteristic equation, because response actually will give you the roots, how where the roots lies on the sigma j omega plane, that will tell you the output response. Now for step input, equation 1 can be written as d square upon omega n square plus 2 xi d by omega n plus 1 whole multiplied by y equal to k xs. This is equation number 2. Now we have introduced a new term which is called differential operator, which is equal to d by dt of this one. That means in this case it will be first term, for suppose for the first term it will be d square y by dt square by omega n square. This will be our first term. Now we should have some initial conditions, because as you know that for solving any differential equations we need some initial condition to solve the equations. The initial conditions are y equal to 0 at t equal to 0, dy by dt equal to 0 at t equal to 0. So with this we can solve this differential equation. Now the particular integral of the equation 2 is equal to yp equal to kxs, but we always look for the transient response also. So only particular integral will not give the complete picture of the response of a system. So the homogeneous solution of this equation will be given by particular integral plus complementary function solution. So particular integral already we have given, this is the particular integral. So we have to find the homogeneous solution. We have to find the complementary function to give the complete solutions of the homogeneous solution for the system. The complementary function will have three possible forms. Case 1, when xi greater than 1, our overdamped system, real unrepeated roots. If you look at the sigma j omega plane, it will look like this. I have sigma j omega plane. So roots will be real unrepeated roots. Fine. A normalized output will be expressed as y upon kxs equal to 1 minus xi plus square root of xi square minus 1 upon 2 square root of xi square minus 1 multiplied by e to the power minus xi plus root over xi square minus 1 into omega n t plus xi minus under the square root xi square minus 1 upon 2 xi square square root of xi square minus 1 e to the power minus xi minus square root of xi square minus 1 into omega n t. You can see here this is our particular integral, and this is this complete, this one along with this one will give you the complementary function. Now if you look at very carefully, you will find this will depend on time. So after some time, when this because of this term negative. So, this will die out, only this y equal to k x s will remain. But we should be interested in the transient response of the system also. That means, because in all the cases we will find what will be the settling time of the systems if you want to find the dynamic error of the system. So, this complementary function is important, because in many cases we will find that I cannot allow the system to get the complete steady state response before it reaches to steady state response. Suppose 5% or 1% of the value, the final value, I have to take some actions. But in some system it is very sluggish, but if it is allowed that within 5% of the final steady state value the reaches, it will take some action, because in instrumentation you know all these measurements, and whether it is you are measuring the temperature, pressure, flow, ultimately you have to utilize this to control some final control element, which mostly are some valves or some heaters which will heat the system, or some boiler temperature, this that. So, this is very important. Now, in case 2, when xi is 1 is a critically damped system, the real repeated roots. How does it look? It looks like that sigma j omega plane. So, real repeated roots, one roots over the other. So, it is critically damped system. So, in that case my normalized output will be y upon k x s equal to 1 minus 1 plus omega n t multiplied by e to the power minus omega n t. Here we also you will find that in the last cases we have, in the case of suppose in the case, if I go back to our original previous slide, you will find some sort of oscillation will come in the case of underdamped systems, because of the, you see the omega n t term is there, I am sorry. So, omega n t term is there, so some oscillation will come, whereas in the case of critically damped system you will find, if I look at the response here, so I have 1 minus this one. So, ultimately the response should look like, so it will go like this and it will go like this one. So, there is no oscillation, but it will take some time before it comes to the steady state conditions, or it is what, because ultimately since it is minus omega n t, you will find this term will die out, only this term will remain. Now, case 3, when xi is greater than 0 and less than 1, we call it underdamped systems, when the roots are complex conjugate roots. What does it mean? It means that in the sigma j omega plane, so this will be our complex conjugate roots. Please note that if it is complex, it must be conjugate, otherwise I cannot realize it by any system, any physical systems. So, if the roots are complex, it must be conjugate, that means it will be, suppose it can be a plus minus j b, this is a real part and this is the imaginary part. Now, the output in this case y upon k x s equal to 1 minus e to the power xi omega n minus xi omega n t 1 minus xi square. Here you can see, I am sorry, that in the case of second order system, in the if it is overdamped or critically damped, there is no question of oscillation. Only in the case of underdamped system, because of this term, you will find the oscillation will come. There will be simple oscillation, after that it will die out. How much will be the oscillations? How many hums you will get, that depends on the value of xi. If the xi is 0.1 or 0.01, you will get large hum, otherwise you will get one. If the xi is 0.7, 0.6 to 0.7, so it will be always just one hum and it will come. So, if I go back, so it will sorry. See, if I go back and have a look in the case of overdamped systems, yes, you see there is no sine term. So, it is overdamped systems, no sine term, so there is no hum, only it will take large time to settle down, but in the case of similarly in the case of critically damped system also there is no question of oscillations, there is no sine term, sinusoidal term, but in the case of underdamped systems, because of this sinusoidal term there will be there will be oscillation. Because of the sine term there will be oscillation. Also there is a phase shift, and the phase shift will be given by sin inverse phi equal to sin inverse under the root 1 minus xi square. So, phase shift will be there in the case of second order system when it is in underdamped, when working as underdamped conditions. Now, mostly we will try to bias our system as second order system as a underdamped system. If you look at very carefully in the analog meters, especially the voltmeters and all those things, you will find, if you look at very carefully to the needle, you will find that when the needle, I have the voltmeters and it is coming, see the needle will be, if you apply some voltage, the needle will go down here, they will make a slight overshoot, then will come back to the original position. That means the where I will take the measurements. If you want to make exactly whenever it is crossing that is you will be wrong, because that is overshoot. So, when it will come back to the original position, that is the position where you take the reading, that is the actual reading, because the overshoot we have done purposefully due to spin and all these things, that it is underdamped systems and the value of the damping coefficient is 0.6 to 0.7. Now, if I look at the response of this system, you see that it come, there is animation, okay, it has come properly. Now, see this is the I made xi less than 1 and this is xi equal to 1 and this is overdamped system. So, this is our overdamped system. This is critically damped system, and this is our underdamped system. Now, how much will be the overshoot? That will depend, and her number of overshoot also depends on the value of xi. And we have plotted the normalized output. Obviously, if it is normalized, it will be maximum value will be always 1. So, there is no question about this one. Now, interesting thing, if you look at the origin of these systems, here you have normalized output omega n t, it does not matter, you can plot t also, because omega n is a constant. So, I mean just the scale factor we have plotted, and here we have plotted also unitless, because we want to plot here unitless, that is the reason we have plotted like this, and this is also unitless. Now, look at the origin of the systems. If you look at the origin, you see there is a S curve, distinct S curve in the system, and this will tell you that even if you do not know whether the system is first order or second order, by looking at the origin I can tell whether it is a first order system or second order system. Well, if the system is underdamped, there is no question, there will be some overshoot, it will come back. So, because if it is a underdamped system, so I will get overshoot and it will come back to original position. It may happen like this also. So, I have a normalized, so it will may go like this. Okay. That means, suppose I have a second order system, there can be several overshoots. So, it will come back, right. So, if it is an underdamped system, always I can tell whether it is a first order system or second order system, because in the case of first order system there will be no overshoot, no resonance. So, there will be no overshoot, but in the case of second order system there will be always overshoot. Now, suppose the system is critically damped, right. Suppose the system is critically damped. In the case of first order system, I will get a response like this, right. So, normalized output, this is omega n t, and in the case of second order system, if it is critically damped, I will get a response like this. So, look at the origin in the two cases. So, since it is it is under, I mean it is not underdamped, it is very difficult to tell, but if somebody, I mean does not tell you what is the system, what is the first or second order, you can tell by looking at the response. there is a distinct S curve at the initial. You look at, if you zoom it, it will look like this one, whereas in the case of first order it will be always like this, right. The reason, there is a distinct reason. If you look at the expressions, you will find, I will leave it to you. If you look at the expressions of the first order and second order systems, you will get your answer. Initially it will go like this, then it will give you all like, whereas here it is initially very high change, then it will go like this. So this is our response. So we will try to make. So you can see that the overdamped system is taking long time. It's taking long time to get the final steady state value, because any instruments, what I want that its response should be 1. So any instruments, if I response is like this, okay. If I am giving a step input, these are all due to step input, is not it? I am giving a step input like this. I want that my output also will look like this. But any physical system, no physical system can have an input like this one, output like this one. There is a lag. So obviously what will happen? So it will take some time. Now you see, this will later on you will see these are plays very important role, that this how much the error, sorry. See, this is the error of measurement. You look at very carefully. Error means that some sort of error has arrived. Suppose at that time t1, that means omega in t1, so some error has arrived, right. Now, so this is important, because sometimes we cannot wait for a long time that when it will reach that particular position. So it will also tell the settling time. We will see the definition of the settling time at the end of the lesson, because always not all necessarily that always you will find that I will allow to have this type of I mean long time to settle down our system. Why it is important? You see, it is also important in the case for underdamped systems. Suppose underdamped systems also what will happen, I will get oscillation. So in that case, suppose if I say that when it will reach 5% of the final steady state value, you take the reading or take the action. So open the control valve, close the control valve. Okay. For many industrial process, please note that the 5% of the final steady state value is quite good for the control. Ultimately, this temperature control or your flow control or pressure control will be reflected in the quality of the product which you are getting. In the case of fertilizer plant, the quality of fertilizer which is coming out. In the case of steel plant, quality of steel it is coming out. So it hardly matters, or it all the management people will not accept that if you make some sensors till it will reach the final steady state value, I can take the action if my quality of the product does not change, even when it reaches 5% of the final steady state, because I know what is my steady state value. So if it reaches 5% of the steady state value, I can take my action, right, because ultimately if the quality, but in some processes, especially in the bio process, you will find the precision, the temperature should be very tightly controlled. So 5% of tolerances cannot be allowed there, because cell will die in that cases. So temperature can be, suppose it is 31 degrees centigrade, I have to maintain it exactly 31 degrees centigrade, or it might be only 30.5 to 31.5. If the temperature goes beyond that range, cell will die. In that situations, I cannot allow this 5% of tolerance band. But for many practical processes or industrial processes like plants, these fertilizers, petrochemicals, steel, we can allow this 5%. That means what I am saying, that within when it is reaches 5%, suppose this is our 5% of the final steady state value, you take action. That means you take the reading, send to the control valve, and whether it is to be open or closed, you take the decisions or stop it, whatever it may be, whatever may be the case. Now, if I look at the ramp input we have seen characteristic equations of a second order system with ramp input can be expressed as follows. Already we have discussed the ramp input in the case of first order system. We are taking same three inputs so that we can compare putting these two side by side. D square upon omega n square plus 2 xi d by omega n plus 1 y equal to k xs dot into t, y equal to dy by dt. equal to 0 at t equal to 0. These initial conditions, we have discussed this before also. What does it mean? Xs dot might mean my input, it looks like this. This is our ramp input. We have discussed thoroughly this when we discuss the first order system, right. Now, this we can do it in the case of second order system. So, this is my input, this constant k as it happened before also, xs dot into t, right. So, it is a continuously changing with time. So, xs dot. So, I made it unitless quantity. So, these are our initial conditions. The solutions are found to be for the case 1 when xi is greater than 1 is overdamped system. So, this is y by k. I have not put excess on the left hand side as it happened in the case of the step input. We have seen that we have done like this, y by k excess. These we have not done. The reason is that we have not done because of the fact that you will find here in this unitless quantity, I have to make it unitless quantity. If I put excess dot here, it will not be unitless, because any value when it is normalized is supposed to be unitless. So, we put excess dot t on the right hand side. So, we put just y, which is output, divided by the static sensitivity on the left hand side and other things on the right hand side. So, this is, as you can see, excess dot t to xi xs dot upon omega n 1 plus in the bracket 1 plus 2 xi square minus 1 minus 2 xi square root xi square minus 1 upon 4 xi under the square root xi square minus 1 multiplied by e minus xi plus root over xi square minus 1 into omega n t plus minus 2 xi square plus 1 minus 2 xi under the square root xi square minus 1 upon 4 xi square root of xi square minus 1 e to the power minus xi minus square root xi square minus 1 into omega n t. Fine. Now, case 2, as it happened before also, it is critically damped system when xi equal to 1. In that case, the output will look like this, y by k xs dot into t minus 2 xs dot by omega n 1 minus e minus omega n t 1 plus omega n t. You can see here these are all unitless, because xs dot by t, omega n is also radians per time. So, these are all becoming unitless. Nowhere you will find that all these term, you can see this steady state, this transient term will die out of the factors, of the minus factors there. Here also for this, whereas in the case of underdamped systems, you will find it is something different. Now, case 3 is a underdamped systems, that means xi is greater than 0, but less than 1, as it happened before also, which is more sought after of systems, because always we make the system the underdamped systems. So, it is y by k xs dot into t minus 2 xi xs dot by omega n in the bracket 1 minus e to the power xi omega n t upon 2 xi under the square root 1 minus xi square sine under the square root 1 minus xi square omega n t plus phi. You can see here that it is xi is 1 minus xi square, because xi is now less than 1, otherwise it will be an imaginary quantity. The phase shift, so I got a phase shift here, and the phase shift is given by tan inverse 2 xi root over 1 minus xi square upon 2 xi square minus 1. Now, ramp response of a second order instrument, there is animation, let it come. You can see here that this is my input, this is input going x equal to xs dot, and we have plotted for different values of xi. These overdamped systems, it taking large time, so the error is also large, and this is for critically damped systems, we can see here, and this is for underdamped system. We have put xi equal to 0.5. So, there is oscillation, quite obviously there is sine term, sinusoidal term, there is oscillation, after that this it will die out. Now, this is our steady state error. We have plotted we have shown the steady state error for a underdamped system, which is 2 xi xs dot upon omega n. This is the steady state error of the system, right, and the time lag of the system, that also we have shown for the underdamped systems, 2 xi by omega n. This is our time lag for the system, this is for this one. So, in the case of overdamped system, so this will be our error and our time lag will be this much in the case of overdamped systems, right. So, obviously we can see that if it is underdamped, after few oscillation it will come, it will start to follow the input. Actually, in fact, this and this should parallel to each other, and asymptotically these two also should be parallel to each other, because at the steady state response all other all the transient part will die out, only the particular integral will remain. So, this is the response of a second order system for a ramp input. Ramp input you won't see, that we will already discussed also, in the case that usually the ramp input will not come, you won't phase the ramp, unlike electrical systems always we give ramp input, like sawtooth waveforms always we know that it is a ramp input which we give in the oscilloscope to synchronize, because in the two vertical plates we give our voltage which we want to measure, and to make the signal stationary we give the sawtooth waveforms on the two horizontal plates. So, the signal appears to be stationary on the screen, whereas in this case the ramp input has not much of significance in the instrumentation, except in some cases, because in many cases you see, because of the large inertias and the spring constant, in many times you will find that even if you are considering the input as a step input, so it won't be a step input to the systems, it will be a ramp input or terminated ramp input. That means, it looks like that I am giving a step input to the system, but the system to the system it will not appear as a step input, it will appear as a terminated ramp input. This is a very good example. Now, you see that all of you must be knowing of the load cell. Load cell we will discuss later on in our of this course. Might be, I do not know what is the exact number of the lesson, but we will cover this in details, these load cells. And those who move in the highways also, you see the load cell also there, because there is a way bridge, because some of the states has restrictions of that how much the load they will carry in the highway. There is some state restrictions and highway restrictions that you cannot. So, usually they want to see some certificate from the wayside road bridge, way bridges where they will wait. The way bridge is nothing but the load cell. Now, when you put on the load cell some weight, so it will never appear as a, even though it is supposed to be a step input, it won't appear as a step input, it will work as a ramp input, even though terminated ramp input, rather, even though we are not much concerned with this transient there, we are more concerned with the steady state response, but the transient is important in the sense that we must know that how long it will take or when it will die out the system, this transient response will die out. For that reasons we must analyze the transient response of the system also. Now, last one is the sinusoidal input, that means we are considering the sinusoidal input to a systems. The sinusoidal input is equal to x equal to xs sin omega t. Say all of us know from the first year classes how the sinusoidal input. So, this is my sinusoidal input. So, this is our xs and this is our x, this is omega t, right, and y by k the output, normalized output, rather y by k by xs equal to sin omega t plus phi 1 minus omega by omega n square upon 2 square plus 4 upon square, sorry, 4 xi square omega square upon omega n square. Here you will find that in this case, that is omega n plays very important role in the case of sinusoidal input, and the frequency is very important, because any systems we must know that what is the frequency limit of the system, that means up to what frequency I can operate our I mean what frequency it will accept. We cannot put like an anti-aliasing filter, that type of things which we usually do in the case of electrical signals, but here always we want that what should be the input. We must determine how much is the input in the system, what is the frequency of the highest frequency of the input to the system which can be tolerated. So, this is our normalized output of the system. So, in fact, what will happen if you take the amplitude, it will be y by k by xs, it will be y by k by xs, and only this part will be the amplitude hour. So, if you look at the normalized output y by k xs, so this will be 1 upon this will be the amplitude hour, because this will not go, right. So, in many you will find that in futures in while you will solve the problems, so I need this type of these values. So, you must remember or you must go through the these notes while you are solving the problems. Now, phase shift in this case, in the case of sinusoidal input, is tan inverse to xi upon omega n minus omega n by omega. Phase shift is also important because any sinusoidal input, if you are measuring some sinusoidal signal, how much is the phase shift of the system you must know. We will see how the phase response will look like. Now, if it is the magnitude response of a first order, I mean second order system for sinusoidal input, it looks like this. Now, even in sinusoidal input, even though it's not very common in nature, but you will find the sinusoidal input in many cases. In vibration analysis, we will find that we are giving their periodic input, not necessarily always sinusoidal, we are giving some periodic input. In biomedical applications, you will find also sinusoidal input. Suppose the variations of the temperature of a patient, so which is who is suffering from the malaria parasites, I mean it is almost a sinusoidal, even though time period is quite large for 24 hours, you will find that a particular temperature will arrive, the patient will get at a particular time of the day. So, that is also sinusoidal input, and some other mode applications we will find in the some sinusoidal, some ambient temperature variation, that is also sinusoidal in nature. So, in the daytime some temperature, night is some other temperatures, in the morning some other temperatures, like this. So, it is sinusoidal input. So, not very uncommon, but even though the period in most of the cases is very large. Unlike electrical systems, any physical systems has mechanical system has a very large time constants of the sinusoidal input. Now, if you look at here, this is the magnitude response of our sinusoidal input. We have plotted here y by k by xs, so xm is 1. You see here interestingly there is large overshoot here. This happens because of the resonance. So, you have to avoid this thing because this is important. That is the reason you see we have plotted here in this case omega by omega n on the x axis side, and we have normalized the x axis also. And you see that here this is the one, that means here is omega equal to omega n. Interestingly, when xi equal to 0, that means damping coefficient is 0. It is very impractical thing. I mean, you cannot make a damping coefficient 0. For academic interests, we should consider this thing. You see that when the damping coefficient is 0, the magnitude becoming infinite, asymptotically infinite. Infinite cannot be because it has some supply. Suppose if I say that if I using an op amp, so you cannot get infinite value. So, it will be limited by the nonlinearity, that is the power plus minus power supply of the op amp. And if I slowly increase the value of xi from 0 to 0.1, my hump is getting reduced. This is xi equal to 0.1. You see I am getting a hump like this one, then it is coming back. It is xi equal to 0.7. We are interested in xi equal to 0.7. We have seen, we told you that in the case of second order systems, any instruments we make usually 0.65 to 0.7. So, I make a xi equal to like this one. So, there is one overshoot, then it comes back, and when it is overdamped systems, xi equal to 2. So, it will look like this one. Now, see here I have not plotted for xi equal critically damped system, it does not matter because it will the response for xi equal to 1, it will be the response should look like this one, something like this. And this roll off you will find always minus 40 dB per decade for a second order system. In the first order system, it will be minus 20 dB per decade, is 40 dB per decade. So, what does it mean actually? What is the significance of this curve? The significance of this curve, it tells that what is the frequency limit of your instrument, of a second order instruments. Suppose in the case of overdamped systems, you can see that there is a large attenuations if you go far off from the origin. Whereas in the case of, if it is xi equal to 0.7, you will find there is a very little, there is a single overshoot, then it comes back. So, that almost horizontal or flat frequency response I am getting. We are not supposed to use it after the omega n, because at the omega n, suppose if it is xi is 0.1, there is a large overshoot. In many instruments it is not allowed to damage the instrument. So, I will, if I know the omega n, so I can limit my frequency response of my instrument. That is the reason it is necessary, we must discuss this point, right. So, as you can see this way, I can see there, let me see. So, here I can tell that here it will looks like this, that the xi decreases, my response, or here in this case xi increases. So, I will get a response like this one. I am more interested at omega equal to omega n. If I look at the phase response of a second order system for sinusoidal input, let it come, all animations, it will take some time. Hopefully it is completed. Now, you see here that if xi equal to 0, that means the damping coefficient is 0. We have already discussed also when the damping coefficient is 0, how my magnitude response will look like. My response will go like this, then go like this one, total discontinuous curve. It will go like this, come like this. Let me go ahead, take it again. It will go like this, xi equal to 0, come like this, and response will be this. From 0 degree, this is 0 degree, to minus 180 degree, it will follow. And if I slowly increase the value of xi, suppose xi I made 0.1, my response will start to look like this one. Similarly, if I xi equal to 1 is critically damped systems, so response will look like this, response will look like this. And if xi equal to overdamped systems, so response will go like this. How? This will go like this. And interestingly, you see, for this is omega equal to omega n, it does not matter what is the value of xi, it will always pass through minus 90 degree at omega equal to omega n. It is more clear if you look back, if I go back to our, sorry. You see here, you see here what happened, that omega equal to omega, I mean when phi equal to tan inverse 2 xi upon omega by omega n minus omega n by omega. You can see here that when omega equal to omega n, always it is minus 90 degree. That is happy, does not depends on the value of xi. Okay, mathematical fallacy will come, all these things, I mean what will be 0 by 0 and all these things. I am not going to, going to details of that thing. Let us go back. Already we have seen this thing. Now, two more terms we will introduce. This is called dynamic error of the system, because we will need this while solving the problems in our future slides. We will see that we will solve some problem first order, second order instruments. Dynamic error dE of a system can be defined as dE equal to y by k by x minus 1, and it represents a measure of the inability of a system to adequately reproduce the amplitude of the input signal for a particular input frequency, right. So, it is inability, that means if you have to look at that what should be the error, obviously it depends on time. If the time goes by, that you will find the error will be getting reduced and reduced, but after certain time if I say that how much is the dynamic error, because this will be utilized to solve some problem, you will find that it is a very important definitions for any physical systems. And measurement systems with a magnitude ratio close to unity over the anticipated frequency band of the input signal is preferred to minimize these. Obviously, we will always try to make d equal to 0, but that we cannot. So, we will take some minimum value of this one. Now, settling time is another important, the characteristics that is used in characterizing the speed of response of an instrument is the settling time. How does it mean? It looks like, you see here, I am sorry, settling time looks like this. I have this one, I am not very, I should draw it nicely. We have discussed this before also. Suppose the 5% of the value, so this is our value T1, so this is the settling time. If you take infinite settling, that does not make any sense. That means after the 5%, when it reaches the 5% of the tolerance band, whatever the time required, that is we call it settling time. This is the time after application of step input for the instrument to reach and stay within a tolerance band around its final value. Now, let us start some problem. So, let us look at the problem 3.1. It says a first order temperature transducer is used to measure the temperature of the oil bath, and if the temperature goes above 100 degrees centigrade, heat supply to the oil bath should be stopped within 5 seconds after reaching 100 degrees centigrade. Determine the maximum allowable time constant of the sensor if the measurement error of 5% is allowed, right. So, let us solve this problem. I do not know, yes, it have chosen properly. Problem looks like this. So, here, okay, let us go back. So, it looks like this, that measurement error will be equal to e to the power minus t by tau. Now, for the given problem, e to the power minus t by tau equal to 0.05 for t less than equal to 5 seconds, tau will become less than equal to 1.66 second. That means the time constants of the system should be less than equal to 1.66 seconds, right. If the time constant of the system is less than equal to 1.66 seconds, so the 5% allowed, I mean after 5 seconds 5% of tolerance band can be allowed, or 5% for the dynamic error can be allowed, right. Now, let us go to problem number 3.2. It tells I will solve here from problem number 3.1 to 3.3, and I will give the problem 3.4 to 3.6 and will explain to some extent 3.4 to 3.6, but the solution will be given at the beginning of the lesson 4. So, I will give some hints. So, you are supposed to solve it of your own. So, the problem number 2 or 3.2 of the lesson 3 will tell that like this. I mean, a first order instrument has a time constant of 0.5 second. It is measuring a process parameter that is a sinusoidal in nature and having a frequency of 3 Hz. Determine the dynamic error of the system. Fine. So, the system is known, it is a first order system, time constant is also known, but the signal is now sinusoidal in nature instead of step and all these things. Frequency is given. So, you have to find the dynamic error of the system. Okay. So, there will be a constant dynamic error in the first order system because this is a phase shift. So, there is a constant dynamic error in the first order system. Here it looks like this. You see here that in the case of first order systems, I can write the dynamic error equal to dE equal to y by k by x minus 1. Here y by k by x equal to 1 upon root over 1 plus omega tau whole square. Here omega is given, omega is 2 pi 3 and tau is equal to 0.5. So, y by k by x will be equal to 1 upon root over 1 plus 2 pi 3 into 0.5 whole square, which is coming, I am showing you the complete calculations which I have calculated, root over 89.7364, which is equal to 1 upon 9.472, which is 0.105. Clear? So, the dynamic error equal to 0.105 minus 1 equal to 0.89 or minus 89%, that is the error, right. This is your answer. Now, let us go to the problem number 3. It is telling that the first order temperature sensor has been suddenly immersed in a liquid that has a temperature of 100 degree centigrade, and it after 3 seconds the sensor shows a temperature of 80 degree centigrade. Calculate the instrument time constant, also calculate the error in the temperature reading after 2 seconds. So, here you see that y equal to, let me take the white page. So, y equal to 100 1 minus e to the power t by tau. So, t equal to 3 second and y t equal to 3 second equal to 80 degree centigrade. So, 80 equal to 100 1 minus e to the power minus 3 by tau. So, after solving I can show you the detailed calculation. So, it is coming 0.8 equal to 1 minus e to the power 3 by tau. So, it is coming around 3 by tau or 3 by tau 2.303 into log of 5. So, it is coming around tau equal to 1.86 second. So, now if I put this is the time constant of the system. Now, if I put y equal to 2 second to 100 1 minus e to the power minus 2 by 1.86 So, equal to 100 1 minus e to the power minus 1.0732. So, it is equal to 100 1 minus 0.341 is equal to 65.8 degree centigrade. So, this is the temperature at after 2 seconds. So, the error will be, you subtract it from 100, or 100 should be subtracted from this, it is minus 34.2 degree centigrade. This is the error, right. Now, problem number 3, I will not make the solution to the problem number 3, which you have to do, and so a pressure transducer is to be selected to measure the pressure of a vessel, and the pressure variation can be considered as a sinusoidal signal, or the frequency lies between 1 and 4 Hz. Several sensors are available, each with known time constant. Select a sensor if the dynamic error of plus minus 1% is acceptable. Now, you see it is first order instrument, so there is no question of taking the plus 1%, because always it will go below, if you remember. So, it is the first order systems, always the sorry. So, so it is first order system, it can never overshoot like this one, it will always go. So, it is always minus 1%, so you should take, and you have to find the time constant of the system, that is your questions, or what is the range of the time constant rather. That means that it will, because it is 1 Hz to 4 Hz. So, this is 1 Hz to 4 Hz. So, within the, if it lies between this, what should be the range of your time constant? This I will solve in the next class. Now, let us look at 3.5. A periodic signal is to be measured with a first order instrument having a time constant of 3 seconds. If the dynamic error of plus minus 5% can be tolerated, phi is the highest frequency of the input signal that can be measured by the instrument. So, in this case, you must see that this is a basically we have considered this as a first order instrument, okay, and you have to find the value of omega, that means the frequency range for which the instrument can be used, right, highest frequency. Now, the last problem you will find is a second order system. So, there is no question. So, if it is a second order system, you have to take both plus and minus of the dynamic error, that is the reason we have given. So, you have to take both, that means you have to take both plus and minus of 6%. So, accordingly you will get the value of the omega n. So, the natural frequency of the sensors you have to find here, you have to find the value of omega n here. So, you try to solve these problems, and the solutions will be given in the next class. And I will remind you that here you see that the problem number 3.4, the instrument is first order. Problem number 3.5, also it is a first order system, whereas problem number 3.6 is a second order system. So, with this I come to the end of the lesson 3.